Mars, and it is, by almost any measure, the most important planet in the solar system other than our own, not the largest. That is Jupiter, not the hottest. That is Venus, not the most beautiful. If rings are your standard of beauty, that is Saturn. Mars is not exceptional in any single physical parameter. It is a small, cold, dry, radiation-blasted world, not from heat, but from the near vacuum that would cause the fluids in your body to vaporize at body temperature. It has no global magnetic field to shield it from the solar wind. It has no oceans, no rivers, no lakes, no liquid water of any kind on its surface today, or at least none that persists for more than fleeting moments under extraordinary conditions. Its average surface temperature is about minus 60 degrees Celsius, colder than anywhere on Earth except the interior of Antarctica during the deepest winter nights. Its gravity is about 38% of Earth's, meaning that a person who weighs 80 kilograms on Earth would weigh about 30 kilograms on Mars. Its day is almost exactly the same length as an Earth day, 24 hours and 37 minutes, which is one of the more remarkable coincidences in planetary science and has no deep physical explanation. Its year is about 687 Earth days, nearly twice as long as ours, because it orbits farther from the Sun. And yet Mars is the planet we have studied most intensively, sent the most spacecraft to, mapped in the greatest detail, analyzed with the most sophisticated instruments, and argued about most passionately. It is the planet most likely to have harbored life in the past, and the planet most likely to be the first world beyond Earth that humans walk upon. It is the planet that has driven more scientific careers, inspired more science fiction, generated more public fascination, and consumed more research funding than any other object in the solar system outside our own world. Everything about Mars matters. Its geology tells us about how rocky planets form and evolve. Its atmosphere tells us about how climates change over billions of years, a subject of more than academic interest given what is happening to Earth's climate right now. Its lost water tells us about the fragility of habitable conditions and how quickly a world can transition. Its soil chemistry tells us about the limits of life and the conditions under which biology might arise. And its future as a potential destination for human settlement tells us something about who we are as a species and what we are willing to risk for the chance to become something more than a single planet civilization. This is everything you need to know about Mars, not a summary, not an overview. Let us start where every story about Mars must start, with the color. The ancient Babylonians, who were among the first systematic astronomers, tracking the motions of celestial objects with a precision that would not be surpassed for over 1,000 years, noticed that this particular wandering star had a reddish tint. They called it Nergal, after their god of war and pestilence and death. The association was not arbitrary. Red was the color of blood, and blood was the color of war, and so the red planet became the war planet, a connection that would persist across cultures and millennia. The ancient Egyptians called it Herdesha, the red one. The ancient Chinese called it the fire star. The Greeks called it Ares, after their god of war. And the Romans, whose names for the planets are the ones we still use, called it Mars, after their own god of war, a deity who was also associated with agriculture and the fertility of the land. A dual nature that turns out to be strangely appropriate for a planet that may once have been fertile and is now barren. The redness of Mars is visible to the naked eye, but through a telescope it becomes vivid and complex. When Galileo first turned his telescope toward Mars in 1610, he saw little more than a reddish disk, too small and too distant to reveal much detail. But as telescopes improved over the following centuries, observers began to see features on the Martian surface. Dark patches that seemed to change with the seasons, bright white caps at the poles that grew and shrank as the Martian year progressed. Faint, linear features that some observers interpreted as canals, engineered waterways built by an intelligent civilization to transport water from the polar ice caps to the arid equatorial regions. The canal hypothesis was championed most vigorously by Percival Lowell, a wealthy American businessman turned astronomer who built his own observatory in Flagstaff, Arizona, in the 1890s specifically to study Mars. Lowell was convinced that Mars was inhabited by an advanced civilization struggling to survive on a drying world, and he spent years mapping an intricate network of canals that he believed crisscrossed the planet's surface. He published his observations and interpretations in a series of popular books that captured the public imagination and cemented Mars's place in popular culture as a world of mystery and potential alien life. Lowell was wrong. The canals were optical illusions, artifacts of the human visual system's tendency to connect discrete dark patches into linear features when observing at the limits of resolution. Other astronomers with equally good telescopes and equally sharp eyes could not see the canals, and by the early 20th century the canal hypothesis was fading among professional astronomers, even as it continued to thrive in science fiction. Wells published The War of the Worlds in 1898, depicting a Martian invasion of Earth by a civilization far more advanced than our own. Edgar Rice Burroughs created Barsoom, a romantic dying Mars populated by warriors and princesses. Ray Bradbury wrote The Martian Chronicles in 1950, imagining human colonists encountering the remnants of a Martian civilization. These fictional depictions shaped public perception of Mars for generations, creating expectations and associations that would influence how people responded to the actual scientific exploration of the planet when it finally began. The scientific exploration of Mars began in earnest in the 1960s, when the space race between the United States and the Soviet Union extended beyond Earth orbit. Mars was an obvious target, the nearest planet whose surface could potentially be observed by a flyby spacecraft, and both nations launched missions toward it as soon as their rocket technology allowed. The early history of Mars exploration is largely a history of failure. The Soviet Union launched its first Mars probe in 1960. It failed to reach Earth orbit. They tried again in 1962, another failure. The United States launched Mariner 3 toward Mars in 1964. Its protective shroud failed to separate, and the spacecraft was lost. 3 weeks later, Mariner 4 was launched, and it succeeded, becoming the first spacecraft to fly past Mars and return close-up photographs of another planet. The images that Mariner 4 sent back in July 1965 were a shock. 22 grainy black and white photographs showing a surface that looked nothing like the canal-crossed world of Lowell's imagination and nothing like the Earth-like world that many scientists had hoped for. Instead, the photographs showed a surface covered in craters looking disturbingly like the moon. There were no canals. There were no signs of vegetation or civilization. There were no oceans or rivers. The surface appeared dead, battered, ancient, and utterly inhospitable. The atmospheric measurements were equally discouraging. Mariner 4's radio signal was used to measure the density of the Martian atmosphere as it passed behind the planet, and the results showed that the atmosphere was far thinner than anyone had expected, with a surface pressure of only about 6 to 7 millibars, less than 1% of Earth's atmospheric pressure. This was too thin to support liquid water on the surface under any temperature conditions. It was too thin to provide meaningful protection from ultraviolet radiation or cosmic rays. The dream of a habitable Mars, or even a potentially habitable Mars, seemed to have died in those 22 photographs. But Mariner 4 had photographed only about 1% of the Martian surface, and it had happened to photograph one of the most heavily cratered regions, the ancient southern highlands. It was like trying to assess the geography of Earth by photographing only the Sahara Desert. Subsequent missions would reveal that Mars was far more varied, far more geologically interesting, and far more tantalizing than those first photographs suggested. Mariner 6 and Mariner 7 flew past Mars in 1969, returning more photographs and more data, but it was Mariner 9 in 1971 that truly transformed our understanding of the planet. Mariner 9 was the first spacecraft to orbit another planet, arriving at Mars on November 14, 1971, and settling into an orbit that would allow it to photograph the entire surface over the course of nearly a year. When it arrived, Mars was engulfed in a global dust storm, one of the largest ever observed, and for weeks the cameras saw nothing but a featureless tan haze with a few dark spots poking through. As the dust began to settle, those dark spots resolved into something extraordinary. They were the summits of enormous volcanoes, projecting above the dust clouds like islands above a sea. The largest of these volcanoes was Olympus Mons, and when the dust finally cleared enough to photograph it in full, it exceeded every expectation. Olympus Mons is the largest known volcano in the solar system. It rises approximately 21.9 kilometers above the surrounding plains, roughly 2.5 times the height of Mount Everest above sea level. Its base is about 600 kilometers across, large enough to cover most of France. The caldera at its summit, the collapsed crater formed by the volcano's own eruptions, is about 80 kilometers wide and nearly 3 kilometers deep, large enough to contain a small country. The entire structure is so vast that if you stood on its flank, you would not be able to see the summit or the base. The curvature of Mars would hide both from view. You would not know you were on a mountain at all. The slope is so gradual, averaging only about 5 degrees, that the horizon in every direction would look like a gently tilting plane. Olympus Mons is a shield volcano, similar in type to the Hawaiian volcanoes on Earth, but vastly larger. On Earth, shield volcanoes are built by the steady accumulation of fluid lava flows, layer upon layer, over millions of years. The Hawaiian chain is formed as the Pacific tectonic plate moves over a stationary hotspot in the mantle, creating a series of volcanoes that grow, move away from the hotspot, go extinct, and are replaced by new ones. This plate motion limits the size of any individual volcano because the plate carries each volcano away from the magma source before it can grow too large. Mars has no plate tectonics. Its lithosphere is a single unbroken shell, and it does not move. When a hot spot in the Martian mantle punches through the crust and begins erupting, the volcano that forms stays directly above the magma source indefinitely. Lava piles up in the same location for hundreds of millions of years, building a structure of almost unimaginable size. Olympus Mons may have been active for more than 1 billion years, and some evidence suggests that the most recent eruptions occurred as recently as 25 million years ago, which in geological terms is practically yesterday. The volcano may not be entirely dead, it may merely be sleeping. Olympus Mons is part of a larger volcanic province called the Tharsis Bulge, a vast uplifted region near the Martian equator that represents one of the most significant geological features in the solar system. The Tharsis Bulge is roughly 4,000 kilometers across and rises about 7 to 10 kilometers above the average Martian surface elevation. It contains several other enormous volcanoes besides Olympus Mons, including Asia Mons, Pavonis Mons, and Ascraeus Mons, 3 shield volcanoes arranged in a neat line along the crest of the bulge, each one roughly the size of the largest volcanoes on Earth. The total volume of volcanic material in the Tharsis region is estimated at about 300 million cubic kilometers, enough to bury the entire surface of Mars to a depth of about 2 kilometers. The formation of Tharsis had profound consequences for the planet. The sheer mass of the volcanic material warped the crust, creating a bulge on one side of the planet that affected everything from the distribution of water to the orientation of the rotational axis. The weight of Tharsis may have caused Mars to tip on its axis, reorienting the entire planet so that the bulge ended up near the equator, where its mass would be in gravitational equilibrium. The volcanic gases released during Tharsis's formation, primarily carbon dioxide and water vapor, would have contributed significantly to the Martian atmosphere, potentially creating conditions warm enough for liquid water to exist on the surface. And the stresses created by the uplift of Tharsis are thought to have cracked the crust, creating the most spectacular geological feature on Mars, and perhaps in the entire solar system. Valles Marineris is a system of canyons that stretches across the Martian surface for more than 4,000 kilometers, roughly the distance from New York to Los Angeles. It is up to 700 kilometers wide in places and up to 7 kilometers deep. For comparison, the Grand Canyon in Arizona is about 446 kilometers long, up to 29 kilometers wide, and about 1.8 kilometers deep. Valles Marineris is not simply a larger version of the Grand Canyon, it is a fundamentally different type of geological feature. The Grand Canyon was carved primarily by the erosion of the Colorado River over millions of years. Valles Marineris was not carved by water, or at least not primarily. It is a tectonic feature, a rift in the crust that formed as the Tharsis bulge rose and the surrounding crust stretched and cracked. It is in essence a place where Mars began to tear itself apart. The canyon system is so large that it is visible from Earth through a good telescope as a dark scar across the face of the planet. Early observers called it Coprates, after the Coprates River in ancient Persia. Mariner 9 revealed its true nature and scale, and it was renamed Valles Marineris in honor of the spacecraft that discovered it. If you could stand on the rim of Valles Marineris and look across, you would not see the other side. The canyon is too wide, the far wall would be beyond the horizon, hidden by the curvature of the planet. You would see only the plunging cliff face below you, dropping away into a haze of dust and distance, and the canyon floor far below, scarred by landslides and layered sedimentary deposits that record billions of years of geological history. In some places, the walls of the canyon expose cross-sections of the Martian crust, revealing layers of rock that date back to the earliest epoch of the planet's history. These exposed layers are a geological treasure, a window into the past that rovers and future human explorers may one day be able to read like the pages of a book. Mariner 9 also revealed something else, something that would prove to be even more consequential than the volcanoes and canyons. It found features that looked like dried river channels. These channels were not the canals of Percival Lowell. They were not straight, they were not evenly spaced. They did not connect the poles to the equator. They were meandering, branching, dendritic networks that looked from orbit exactly like river systems on Earth. They had tributaries, they had floodplains, they had teardrop-shaped islands that form when flowing water divides around obstacles. They had braided patterns characteristic of rivers carrying heavy sediment loads. In some places they emerged from the southern highlands and flowed northward into the low-lying northern plains, depositing sediment in fan-shaped deltas at their mouths. The implications were staggering. Mars today is a frozen desert where liquid water cannot exist on the surface. But these channels indicated that liquid water had once flowed across the surface in enormous quantities, carving valleys hundreds of kilometers long and tens of kilometers wide. Some of the outflow channels were so large that they dwarfed anything on Earth, suggesting catastrophic floods of a scale that has no terrestrial analog. The circumcrized channels, for example, appear to have been carved by floods that released water at rates of millions of cubic meters per second, comparable to the total flow of all the rivers on Earth combined, concentrated in a single short-lived cataclysmic event. Where did this water come from? Where did it go? How long did it flow? Was Mars once warm enough for rain? Did it have oceans? These questions, raised by Mariner 9's photographs in the early 1970s, have driven Mars exploration ever since. They are still not fully answered, but we know vastly more than we did 50 years ago, and the picture that has emerged is both fascinating and sobering. Mars almost certainly had liquid water on its surface in the distant past. The evidence is overwhelming and comes from multiple independent lines of observation. First, the geomorphological evidence. The valley networks, outflow channels, and delta deposits discovered by Mariner 9 have been confirmed and studied in far greater detail by subsequent missions. The Mars Global Surveyor, which orbited Mars from 1997 to 2006, mapped the entire surface at high resolution and revealed thousands of features consistent with water erosion. The Mars Reconnaissance Orbiter, which arrived in 2006 and continues to operate, carries a camera called HEREYES that can resolve features as small as 30 centimeters across from orbit, revealing details of ancient river channels, lake beds, and sedimentary deposits with stunning clarity. The European Space Agency's Mars Express, orbiting since 2003, has provided additional high-resolution imaging and mineralogical data. Together, these orbiters have shown that water-carved features are widespread across the Martian surface, concentrated in the ancient southern highlands, but present in other regions as well. Second, the mineralogical evidence. Water does not just shape landscapes, it alters the chemistry of rocks. When water interacts with volcanic rocks, it produces specific minerals, clays and sulfates and carbonates and hydrated silicates that can only form in the presence of liquid water. These minerals have been detected across large areas of Mars from orbit, using spectrometers that identify minerals by their characteristic absorption of infrared light, and on the surface by rovers equipped with chemical analysis instruments. The Mars rovers Spirit, Opportunity, and Curiosity have all found minerals that require water to form. Curiosity, exploring Gale Crater since 2012, has found mudstones, clay minerals, and sedimentary rocks that were clearly deposited in a lake that once filled the crater. The evidence is not ambiguous. Gale Crater contained a long-lived lake, fed by rivers flowing in from the crater rim, with water that was chemically suitable for life as we know it. The lake may have persisted for millions of years. Third, the isotopic evidence. The ratio of hydrogen to its heavier isotope deuterium in the Martian atmosphere provides clues about how much water Mars has lost over time. Deuterium is twice as heavy as hydrogen, and when water molecules at the top of the atmosphere are broken apart by ultraviolet light, the lighter hydrogen atoms escape into space more easily than the heavier deuterium atoms. Over time, this preferential loss of hydrogen enriches the remaining water in deuterium. The current Martian atmosphere has a deuterium to hydrogen ratio about 5 to 8 times higher than Earth's, indicating that Mars has lost a substantial fraction of its original water inventory to space. Working backward from the current ratio, scientists estimate that early Mars may have had enough water to cover the entire surface to a depth of several hundred meters if spread evenly, roughly equivalent to the volume of Earth's Arctic Ocean. Fourth, the direct detection of water ice. Mars still has water. It is not liquid, and it is not on the surface in most places, but it is there. The polar ice caps contain enormous quantities of water ice. The North Polar Cap is a dome of water ice roughly 1,000 kilometers across and up to 3 kilometers thick, covered by a thin layer of frozen carbon dioxide during winter. The South Polar Cap has a permanent covering of carbon dioxide ice over a layer of water ice that may be even larger than the northern cap. Together, the polar caps contain enough water to cover the entire planet to a depth of about 30 meters if melted and spread evenly, but the polar caps are not the only reservoirs. Radar soundings from Mars Express and the Mars Reconnaissance Orbiter have detected massive deposits of water ice buried beneath the surface at mid-latitudes, preserved under layers of dust and rock. The Phoenix lander, which touched down near the North Pole in 2008, directly observed water ice beneath a thin layer of soil, watching it sublimate in the Martian sunlight over the course of days. And in 2018, a team using radar data from Mars Express announced the detection of what appeared to be a lake of liquid water beneath the South Polar ice cap about 1.5 kilometers below the surface, roughly 20 kilometers across. The claim is controversial. Some scientists argue that the radar reflections could be produced by other materials, such as certain types of clay or volcanic rock, without requiring liquid water. The temperatures at that depth are estimated to be well below the normal freezing point, and liquid water would require either high salt concentrations which lower the freezing point or some other mechanism to remain liquid. The question remains open, and additional data and analysis are needed to settle it. The big question, the question that hangs over all of Mars science like a shadow, is whether Mars was ever truly warm and wet in the way that Earth is warm and wet, with a thick atmosphere, a stable water cycle, rainfall, rivers and oceans, or whether the water features we see were created by transient, catastrophic events, brief episodes of flooding powered by volcanic eruptions or asteroid impacts that temporarily melted subsurface ice, with the water freezing or evaporating almost as quickly as it appeared. This question is not merely academic, it goes to the heart of whether Mars was ever habitable for life as we know it. Life on Earth requires liquid water, not just occasionally, not just in brief catastrophic pulses, but persistently over geologically significant timescales. Life needs time to originate and evolve. If Mars had stable bodies of liquid water for millions or billions of years, the chances that life arose there are considerably higher than if the water was only present in fleeting episodes. The current scientific consensus, based on decades of orbital and surface observations, is somewhere between the two extremes. Early Mars, during the first billion years or so of the planet's history, was almost certainly warmer and wetter than it is today. The valley networks in the southern highlands, which are the features that most closely resemble Earth's river systems, date to this early period, roughly 3.5 to 4 billion years ago, a time known as the Noachian epoch. The geological evidence suggests that during the Noachian, Mars had a thicker atmosphere, possibly with enough greenhouse warming to support standing bodies of water, at least intermittently. Rainfall may have occurred, at least in some regions, at least some of the time. Lakes, and possibly even the Northern Ocean, may have existed, though the evidence for a global ocean remains debated. But even during this warmer, wetter period, Mars was probably not Earth-like in the way we might imagine. It was likely cold by Earth standards, with temperatures hovering near the freezing point much of the time. The atmosphere was thicker than today, but still much thinner than Earth's. The Sun was about 30% dimmer 4 billion years ago than it is now, which made keeping Mars warm even harder. The warming may have been episodic, driven by volcanic eruptions that injected greenhouse gases into the atmosphere, followed by cold intervals when the gases were removed by chemical reactions with surface rocks. Mars may have cycled between relatively warm, wet periods and cold, dry periods multiple times during the Noachian, with each warm period lasting thousands or millions of years before giving way to a freeze after the Noachian roughly 3 to 3.5 billion years ago. Mars appears to have undergone a fundamental transition. The thick atmosphere was gradually lost. The surface water froze or evaporated, and the planet entered the cold, dry state that persists today. This transition was not instantaneous. It played out over hundreds of millions of years, and the reasons for it are bound up with one of the most important differences between Mars and Earth. Earth has a global magnetic field generated by convection currents in its liquid iron outer core, a process called the geodynamo. This magnetic field extends far into space, creating a protective magnetosphere that deflects the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. Without the magnetosphere, the solar wind would gradually strip away Earth's atmosphere, breaking apart molecules in the upper atmosphere and carrying the fragments into space. Venus, which has no global magnetic field, has lost most of its original water through this process, though its thick carbon dioxide atmosphere has persisted because CO2 is heavier and harder to strip away. Mars once had a global magnetic field. We know this because the Mars Global Surveyor magnetometer detected strong localized magnetic fields in the ancient crust of the southern highlands. These crustal magnetic anomalies are remnants of an ancient global field frozen into the rocks when they solidified in the presence of that field billions of years ago, like a fossil recording the direction and strength of the field at the time the rock formed. Mars is smaller than Earth, with about 11% of Earth's mass and about 15% of its volume. Smaller planets cool more quickly because they have a higher surface area to volume ratio, losing heat to space more efficiently. As Mars's core cooled, the convection currents that generated the magnetic field weakened and eventually stopped. The dynamo shut down and the protective magnetic field collapsed. Without a magnetic field, Mars was exposed to the full force of the solar wind. Over hundreds of millions of years, the solar wind gradually stripped away the Martian atmosphere, molecule by molecule, ion by ion. The process was slow but relentless. The NASA MAVEN spacecraft, which has been orbiting Mars since 2014, specifically to study atmospheric loss, has measured the rate at which the atmosphere is currently being lost to space, and has used those measurements to estimate how much has been lost over the planet's history. The results suggest that Mars has lost the majority of its original atmosphere to space, going from a surface pressure that may have been comparable to Earth's, perhaps half a bar to 1 bar, to the current pressure of about 6 millibars. As the atmosphere thinned, the greenhouse warming it provided diminished, temperatures dropped, and the surface water froze. Some of the water was lost to space along with the atmosphere. Some was incorporated into the polar ice caps. Some seeped into the subsurface and froze there, forming a global cryosphere, a shell of frozen ground that may contain enormous quantities of ice. The loss of Mars's atmosphere is one of the most important stories in planetary science because it illustrates how fragile habitable conditions can be. Mars started with many of the same ingredients as Earth: a rocky surface, a substantial atmosphere, abundant water, volcanic activity, possibly a magnetic field. But because it was smaller, it cooled faster, lost its magnetic field sooner, and had its atmosphere stripped away. The result is the Mars we see today, a world that was once potentially habitable and is now one of the most hostile environments in the solar system for life as we know it. This story has direct implications for our understanding of habitability in the universe. It tells us that having the right ingredients is not enough. A planet also needs to maintain the right conditions over geological timescales. Size matters. A planet's mass and composition determine how quickly it cools, how long it retains its magnetic field, how effectively it holds onto its atmosphere. Location matters. A planet's distance from its star determines how much solar radiation it receives, how quickly its atmosphere is eroded by the stellar wind, how warm its surface can be. Timing matters. The same planet at a different epoch in its star's history might have very different conditions as the star's luminosity and particle output change over billions of years. Mars teaches us that habitability is not a permanent state. It is a window that can open and close, and for Mars it appears to have closed relatively early, within the first billion years or so of the planet's 4.6 billion year history. Whether life arose during that window is the question that drives much of current Mars exploration. The search for life on Mars, past or present, has been a central goal of Mars exploration since the Viking missions of the 1970s, which represent one of the most ambitious and controversial chapters in the history of space science. The Viking program consisted of 2 spacecraft, each comprising an orbiter and a lander. Viking 1 landed on the surface of Mars on July 20, 1976, becoming the first spacecraft to successfully operate on the Martian surface. Viking 2 landed on September 3, 1976, at a different location about 6,500 kilometers away. Both landers carried cameras that returned the first photographs from the surface of Mars, showing a landscape of rusty red rocks and fine-grained soil under a pinkish sky, the color produced by fine dust suspended in the thin atmosphere. The Viking landers also carried 3 biology experiments specifically designed to test for microbial life in the Martian soil. These experiments were the culmination of years of planning and represented the first and, for a long time, the only direct attempt to detect life on another planet. The most famous of these experiments was the labeled release experiment designed by Gilbert Levin. The experiment worked as follows. A sample of Martian soil was placed in a sealed chamber and a nutrient solution containing organic compounds labeled with radioactive carbon-14 was added. If living microorganisms were present in the soil, they would presumably metabolize the nutrients, breaking them down and releasing carbon-14 as radioactive carbon dioxide gas, which could be detected by a radiation counter inside the chamber. A control experiment was also run, in which a soil sample was first sterilized by heating to 160 degrees Celsius to kill any organisms, then treated with the same nutrient solution. If the response in the unheated sample was due to biology, the sterilized sample should show no response. The results were startling. The unheated soil produced a strong immediate release of radioactive gas, exactly as you would expect if living organisms were metabolizing the nutrients. The sterilized control sample produced no such release by the criteria established before the mission. This was a positive result for life. But the other 2 biology experiments told a different story. The gas exchange experiment, which looked for changes in the gases above a soil sample when nutrients were added, produced ambiguous results that were difficult to interpret as biological. And the pyrolytic release experiment, which looked for organisms that could incorporate carbon from the Martian atmosphere into organic molecules, produced results that were at best marginally positive. Most critically, the Viking gas chromatograph mass spectrometer, which analyzed the soil for organic molecules, found none, not even trace amounts. The Martian soil, at least at the Viking landing sites, appeared to be completely devoid of organic material. This was astonishing and deeply problematic for the life hypothesis on Earth. Organic molecules are everywhere, produced by both biological and non-biological processes. Even in the most sterile terrestrial environments, organic molecules can be detected. Their complete absence from the Martian soil suggested either that life was not present or that some powerful chemical process was destroying organic molecules at the surface. The scientific consensus that emerged after the Viking missions was that The labeled release results were not evidence of life, but rather the product of a non-biological chemical reaction in the highly oxidizing Martian soil. The leading hypothesis was that the soil contained reactive oxidizing compounds, possibly perchlorates or hydrogen peroxide, that reacted vigorously with the organic nutrients, producing gas without any biological involvement. The sterilization step would destroy these reactive compounds, explaining why the heated control showed no response. The absence of organic molecules was consistent with this interpretation. If the soil chemistry was oxidizing enough to destroy all organic compounds, it was oxidizing enough to produce a false positive in the labeled release experiment. Gilbert Levin disagreed with this interpretation for the rest of his life. He maintained that his experiment had detected life on Mars, and that the absence of organics detected by the mass spectrometer was due to the instrument's limited sensitivity rather than the actual absence of organics. The debate was never fully resolved during Levin's lifetime, and it continues in modified form today. The Viking biology results remain one of the most controversial episodes in the history of planetary exploration, a reminder of how difficult it is to design experiments that can unambiguously distinguish biology from chemistry on a world whose chemistry we do not fully understand. Decades later, the question of organics on Mars was revisited by the Curiosity rover. Curiosity's sample analysis at Mars Instrument, a far more sophisticated chemical laboratory than anything Viking carried, has detected organic molecules in Martian rocks and soil, not in huge quantities, but unambiguously present. These include simple organic compounds like chlorobenzene and dichloroalkanes, as well as more complex molecules including thiophenes and other sulfur-bearing organics. The discovery does not prove that life exists or ever existed on Mars. Organic molecules can be produced by non-biological processes, including reactions in interstellar space, delivery by meteorites and comets, and geochemical reactions in volcanic rocks, but it does resolve one part of the Viking mystery. Organics are present on Mars. Viking probably did not detect them because the heating process used by its instrument, combined with the perchlorates in the soil, destroyed the organic molecules before they could be measured. The absence was an artifact of the experimental method, not a real absence. The detection of perchlorates in the Martian soil was itself a significant discovery made by the Phoenix lander in 2008. Perchlorates are salts of perchloric acid, powerful oxidizing agents that are relatively rare on Earth but apparently abundant on Mars. Their presence has implications for both the search for life and for future human exploration. Perchlorates could serve as an energy source for hypothetical Martian microorganisms, as some terrestrial bacteria can use perchlorates as an electron acceptor in their metabolism. But perchlorates are also toxic to human thyroid function at high concentrations, meaning that Martian soil, if ingested or inhaled, could pose a health risk to future human explorers. Any human settlement on Mars would need to deal with perchlorate contamination of the soil, either by removing it or by avoiding direct exposure. The search for life on Mars has shifted in recent years from looking for life on the present-day surface, which is probably too hostile for any organism we can imagine, to looking for evidence of past life in ancient rocks and for present-day life in subsurface environments where conditions might be more favorable. The subsurface is particularly intriguing because it could offer protection from the intense ultraviolet radiation that bathes the Martian surface, temperatures above freezing if geothermal heat is sufficient, and possibly liquid water if the conditions are right. On Earth, thriving microbial communities exist kilometers below the surface, living in the pore spaces of rocks, metabolizing chemical energy from the rocks themselves, completely independent of sunlight. If similar communities exist on Mars, they would be extremely difficult to detect from the surface or from orbit. Finding them might require drilling, and drilling on Mars is technically challenging and has not yet been attempted at the depths that would be necessary. The Perseverance rover, which landed in Jezero crater in February 2021, represents the most sophisticated attempt yet to search for evidence of past life on Mars. Jezero crater was chosen as a landing site because orbital images clearly show a river delta at the crater's western rim, a fan-shaped deposit of sediment where an ancient river once flowed into a lake that filled the crater. On Earth, river deltas are among the best environments for preserving biosignatures, the chemical or physical traces left by living organisms. Fine-grained sediments deposited in calm, standing water can trap and preserve organic molecules, microfossils, and other evidence of life for billions of years. Perseverance carries a suite of instruments designed to search for biosignatures in the rocks of Jezero crater. Its Sherlock instrument uses ultraviolet lasers to detect organic molecules and determine their spatial distribution within rocks. Its Pixel instrument uses X-ray fluorescence to determine the elemental composition of rocks at a fine scale. Its Mastcam-Z cameras can image rock textures at high resolution, looking for structures that might be biological in origin, such as stromatolites, the layered structures built by microbial communities that are among the oldest evidence of life on Earth. But Perseverance has another mission that is arguably even more important. It is collecting rock samples, drilling cores from carefully selected rocks, and sealing them in titanium tubes to be left on the Martian surface for retrieval by a future mission. These samples are intended to be returned to Earth, where they can be analyzed in terrestrial laboratories with instruments far more powerful and versatile than anything that can be sent to Mars. The Mars Sample Return Mission, a joint effort by NASA and the European Space Agency, has been planned for years, though its timeline, budget, and design have been repeatedly revised. If it succeeds, it will return the first samples from another planet to Earth, allowing scientists to study Martian rocks with the full arsenal of terrestrial analytical techniques. The potential for discovery is enormous. A single returned sample could contain definitive evidence of past life, or it could rule it out for the specific environment sampled. Either result would be transformative. The question of whether Mars ever had life or still has life is not just a scientific question, it is a philosophical one. If life arose independently on Mars, it would mean that the origin of life is not a singular, miraculous event that happened only once in the history of the universe. It would mean that life arises readily wherever conditions are suitable, that the universe is likely teeming with biology, that we are not alone in any meaningful sense. Even if the life is nothing more than single-celled microorganisms, the mere fact of its independent origin would revolutionize our understanding of our place in the cosmos. Conversely, if Mars was habitable for hundreds of millions of years and life never arose, that would also be profoundly significant. It would suggest that the origin of life is far more difficult and improbable than we thought, that habitable conditions are necessary but not sufficient, and that life on Earth might be rarer than our most conservative estimates. Let me describe the surface of Mars as we understand it today, because the landscape is one of the most extraordinary in the solar system, and understanding it is essential to understanding the planet. Mars has two fundamentally different types of terrain, divided roughly along the planet's equator. The southern hemisphere is dominated by heavily cratered highlands, the oldest surfaces on the planet, dating back to the Noachian epoch, more than 3.5 billion years ago. These highlands are elevated, on average, several kilometers above the reference datum, the Martian equivalent of sea level. They are pocked with craters of all sizes, from tiny bowl-shaped depressions to vast impact basins hundreds of kilometers across. The largest impact basin in the southern hemisphere is Hellas Planitia, a colossal structure roughly 2,300 kilometers in diameter and more than 7 kilometers deep, the deepest point on the Martian surface. Hellas was created by a massive asteroid impact early in Mars's history, and the force of the impact was so great that the shock wave may have traveled through the planet and caused disruption on the opposite side. The northern hemisphere is strikingly different. It is dominated by smooth, low-lying plains on average several kilometers below the datum, with far fewer craters than the southern highlands. The contrast between the two hemispheres is one of the most prominent features of Mars's geography and one of the most debated topics in Martian geology. This hemispheric dichotomy, as it is called, has been known since the Mariner missions, and its origin remains uncertain. The most popular hypothesis is that the northern lowlands were created by a single giant impact early in Mars's history, the largest impact in the inner solar system, which excavated a basin covering most of the northern hemisphere and stripped away the older cratered surface. If this hypothesis is correct, the impactor would have been roughly 2,000 kilometers across, comparable in size to Pluto, and the impact would have occurred within the first few 100 million years of Mars's existence. Alternative hypotheses invoke mantle convection processes or a combination of impacts and internal dynamics, and the question remains open. The difference in elevation between the two hemispheres is significant for the question of ancient water. If Mars ever had a large body of water, an ocean, it would naturally have pooled in the lowest regions, the northern lowlands. And indeed, some researchers have identified features along the boundary between the highlands and the lowlands that they interpret as ancient shorelines, including step terraces, wave-cut platforms, and sedimentary deposits consistent with a standing body of water. The evidence for a northern ocean is debated, with some scientists finding the shoreline features convincing and others pointing out that the proposed shorelines do not maintain a consistent elevation as they should if they were carved by a single body of water. The discrepancy might be explained by later deformation of the surface, tilting of the crust by volcanic loading or polar wander, or by the ocean having different sizes at different times. The question of whether Mars once had a northern ocean is one of the great unsettled issues in Mars science. The Martian surface is covered with a layer of fine-grained material called regolith, produced by billions of years of bombardment by meteorites, cosmic rays, ultraviolet radiation, and wind erosion. The regolith is typically several meters thick and consists of pulverized rock, mineral fragments, and the iron oxide dust that gives Mars its red color. The iron oxide, primarily in the form of the mineral hematite and the poorly crystalline nanophase oxide that coats virtually everything, was produced by the oxidation of iron-bearing minerals in the surface rocks. The iron was originally locked in silicate minerals like olivine and pyroxene in the volcanic basalt that makes up most of the Martian crust. Over billions of years, exposure to the oxidizing environment, possibly involving water in the past and reactive peroxides in the present, converted the iron from its reduced state in the silicate minerals to its oxidized state in iron oxide. Mars is red because it is rusted. The dust is extraordinarily fine, with typical grain sizes of a few micrometers, smaller than the particles in cigarette smoke. This fineness is what allows it to be lofted into the atmosphere by even modest winds and to remain suspended for weeks or months. Martian dust storms are among the most dramatic meteorological phenomena in the solar system. Local and regional dust storms occur frequently, raising clouds of dust that can obscure large areas of the surface, but occasionally the storms grow to global proportions, engulfing the entire planet in a thick haze that can persist for months. The 1971 global dust storm that greeted Mariner 9 was one example. Another occurred in 2018, and it was this storm that killed the Opportunity rover by coating its solar panels with so much dust that the rover could no longer generate enough power to survive. The Martian atmosphere deserves detailed attention because it is central to understanding the planet's past, present, and future. The atmosphere is composed of about 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, and traces of oxygen, carbon monoxide, water vapor, and other gases. The surface pressure averages about 6.1 millibars, roughly 0.6% of Earth's surface pressure. This is just above the triple point of water, the minimum pressure at which liquid water can exist. Below the triple point, water can exist only as ice or vapor, transitioning directly between the two states without passing through a liquid phase. The fact that the Martian surface pressure is so close to the triple point means that under certain conditions in the warmest locations at the lowest elevations during the warmest part of the day, liquid water might briefly exist on the surface, but these conditions are marginal and transient. Any liquid water that formed would evaporate within minutes or hours. Stable, long-lived bodies of liquid water are not possible under current Martian atmospheric conditions. The thin atmosphere has another important consequence. It provides almost no thermal insulation. On Earth, the atmosphere acts as a blanket, trapping heat through the greenhouse effect and moderating temperature swings between day and night. On Mars, the atmosphere is too thin to retain much heat. Daytime temperatures near the equator can reach a relatively balmy 20 degrees Celsius in summer, but at night, temperatures at the same location can plunge to minus 80 degrees or lower. The diurnal temperature range on Mars can exceed 100 degrees Celsius compared to a typical range of 10 to 20 degrees on Earth. A Martian day begins and ends with extreme cold, with only a few hours of relatively moderate temperatures around midday. The atmosphere also provides almost no protection from ultraviolet radiation. Earth's ozone layer absorbs the most harmful ultraviolet wavelengths, protecting the surface from radiation that would damage DNA and other biological molecules. Mars has no ozone layer, and its thin atmosphere provides minimal UV absorption. The Martian surface is bathed in intense ultraviolet radiation that would be lethal to most terrestrial organisms, combined with the oxidizing soil chemistry. The high UV flux makes the present-day Martian surface an extremely hostile environment for life. Any organisms on Mars today would almost certainly need to be underground, shielded from radiation by at least a meter or two of rock or soil. Despite its thinness, the Martian atmosphere is meteorologically active. Winds on Mars can reach speeds of 100 kilometers per hour or more, though because the atmosphere is so thin, even these high winds exert very little force. A 100 kilometer per hour wind on Mars would feel like a gentle breeze on Earth, pushing on you with only a few percent of the force of the same wind speed in Earth's denser atmosphere. The dramatic sandstorms depicted in some Mars fiction, powerful enough to topple structures or endanger spacecraft, are not realistic. The winds can move dust but cannot move rocks or exert significant mechanical force on large objects. The greatest danger from Martian dust storms is not the wind itself, but the dust that obscures the sun and coats solar panels, as Opportunity discovered to its cost. Mars has seasons caused by the tilt of its rotation axis, which is about 25.2 degrees, very close to Earth's 23.4 degree tilt. This similarity in axial tilt means that the pattern of seasons on Mars is broadly similar to Earth's. The northern hemisphere has spring, summer, autumn, and winter, just as Earth does, with the same general pattern of longer days and warmer temperatures in summer and shorter days and cooler temperatures in winter. But Mars's orbit is considerably more eccentric, more elliptical, than Earth's. Mars's distance from the Sun varies from about 207 million kilometers at perihelion, its closest approach, to about 249 million kilometers at aphelion, its farthest point. This 42 million kilometer variation means that the amount of solar energy Mars receives varies by about 40% over the course of its orbit, a much larger variation than Earth experiences. This orbital eccentricity affects the seasons asymmetrically. Southern Hemisphere summers, which coincide with perihelion, are significantly warmer than Northern Hemisphere summers. Southern winters are correspondingly colder. This asymmetry is thought to be one of the reasons why global dust storms tend to occur during southern summer, when the stronger solar heating creates more vigorous atmospheric circulation and lifts more dust into the atmosphere. The seasonal cycle also drives a remarkable phenomenon involving the polar ice caps. The caps are made of two components: a permanent layer of water ice that persists year-round, and a seasonal layer of frozen carbon dioxide, dry ice, that forms during winter and sublimates, transitions directly from solid to gas during spring. During winter at each pole, the temperature drops low enough for carbon dioxide to freeze out of the atmosphere, forming a layer of dry ice up to a meter thick that extends from the pole to latitudes of about 50 to 60 degrees. This process removes a significant fraction of the total atmospheric carbon dioxide, causing the atmospheric pressure to drop by about 25% during winter at each pole. When spring arrives and the dry ice sublimates, the CO2 is returned to the atmosphere and the pressure rises again. This seasonal cycling of carbon dioxide between the atmosphere and the polar caps is the largest single meteorological process on Mars, involving the transfer of roughly a quarter of the planet's entire atmosphere between the surface and the sky twice every Martian year. The sublimation of the polar dry ice in spring produces some of the most visually striking features on Mars. As the seasonal ice layer warms from below, trapped carbon dioxide gas creates pockets of high pressure beneath the ice. When the pressure exceeds the strength of the ice, it erupts in geysers, jets of CO2 gas carrying dark basaltic dust from beneath the ice, depositing fan-shaped patterns of dark material on the bright ice surface. These fans, visible from orbit as dark streaks radiating from points on the ice cap, were initially mysterious. Some early interpretations suggested they might be biological colonies of photosynthetic organisms emerging from beneath the ice as spring arrived. Further analysis has shown conclusively that they are produced by the physical process of gas eruption, not by biology, but they remain among the most dramatic seasonal changes observed on any planet. Mars has 2 moons, and they are among the strangest objects in the solar system. Phobos and Deimos are tiny, irregularly shaped bodies that orbit Mars at very close range. They look nothing like Earth's moon. They are not spherical. They are not large enough for their own gravity to have pulled them into round shapes. They look like lumpy potatoes, dark and cratered and battered, more like captured asteroids than moons in any conventional sense. Phobos, the larger of the two, is roughly 27 by 22 by 18 kilometers, about the size of a large city. It orbits only 6,000 kilometers above the Martian surface, closer to its parent planet than any other known moon in the solar system. At this distance, Phobos orbits faster than Mars rotates, completing one orbit every 7 hours and 39 minutes. This means that from the Martian surface, Phobos rises in the west and sets in the east, moving visibly across the sky over the course of a few hours. It is close enough that it appears noticeably different in size depending on where on Mars you observe it from, and it is close enough that an observer on the equator sees it from a significantly different angle than an observer near the poles. Phobos is also doomed. Its orbit is slowly decaying due to tidal interactions with Mars. Every century it moves about 1.8 meters closer to the planet. In roughly 50 million years, it will either crash into Mars or, more likely, be torn apart by tidal forces as it crosses the Roche limit, the distance at which the tidal forces from the parent planet exceed the gravitational cohesion of the Moon. The resulting debris would form a ring around Mars, a temporary ring that would eventually rain down onto the surface over millions of years. Mars may have had rings in the past formed by the destruction of earlier moons, and the cycle of moon formation and destruction may have repeated several times over the planet's history. Phobos has a prominent feature called Stickney, a crater roughly 9 kilometers in diameter, so large relative to the Moon that the impact that created it must have come close to shattering Phobos entirely. Grooves and linear fractures radiate outward from Stickney across much of the surface, possibly stress fractures from the impact or possibly produced by tidal forces from Mars. Deimos is smaller, roughly 15 by 12 by 11 kilometers, and orbits much farther out, at about 20,500 kilometers from Mars, with an orbital period of about 30 hours. From the Martian surface, Deimos appears as a bright, slowly moving star, barely showing a disk to the naked eye. It rises in the east and sets in the west, like a normal celestial object, but it moves so slowly across the sky that it takes more than 2 days to cross from horizon to horizon. The origin of Phobos and Deimos is debated. Their dark, carbon-rich surfaces resemble certain types of asteroids, leading to the hypothesis that they are captured asteroids, objects from the asteroid belt that wandered too close to Mars and were trapped by its gravity. But capturing an asteroid into a stable, nearly circular orbit like those of Phobos and Deimos is dynamically difficult without some mechanism to dissipate energy, and the nearly equatorial, nearly circular orbits of both moons are hard to explain by capture alone. Alternative hypotheses suggest that the moons formed from debris produced by a large impact on Mars, or that they coalesced from a ring of material around the planet. The Japanese space agency JAXA is planning a mission called Martian Moons Exploration, or MMX, scheduled for launch in the mid-2020s, which will visit Phobos, collect samples from its surface, and return them to Earth. Analysis of these samples should help determine whether Phobos is a captured asteroid or something that formed in place around Mars. Let me talk about the robots that are on Mars right now, because Mars is the only planet in the solar system that is inhabited entirely by robots. And the story of how they got there and what they have found is one of the great adventures of human exploration. As of today, there are 2 operational rovers on the surface of Mars and 3 operational orbiters circling above. The rovers are Curiosity, which has been exploring Gale Crater since August 2012, and Perseverance, which has been exploring Jezero Crater since February 2021. Perseverance is accompanied by Ingenuity, a small helicopter that made history by becoming the first aircraft to achieve powered-controlled flight on another planet. Curiosity is a car-sized rover about 3 meters long and weighing about 900 kilograms, powered by a radioisotope thermoelectric generator that converts the heat from decaying plutonium-238 into electricity. This power source gives Curiosity a significant advantage over solar-powered rovers, which are limited by dust accumulation and seasonal variations in sunlight. Curiosity can operate day and night in any season regardless of dust storms. It has been driving, drilling, analyzing, and photographing the Martian surface for more than a decade, covering over 30 kilometers, and it is still going. Curiosity's primary mission was to determine whether Gale Crater ever had conditions suitable for microbial life, and it answered that question decisively within its first year. The rover found mudstones at the bottom of Gale crater that were deposited in a freshwater lake that existed roughly 3 to 3.5 billion years ago. The water was chemically neutral, not too acidic or too alkaline. It contained the key chemical elements needed for life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The lake persisted for at least hundreds of thousands of years, possibly millions. The conditions were, by any reasonable standard, habitable. Since that initial discovery, curiosity has been driving up the flanks of Mount Sharp, a 5-kilometer tall mound of layered sedimentary rock in the center of Gale crater. The layers of Mount Sharp record the environmental history of the crater over billions of years, with the oldest layers at the bottom and the youngest at the top. By driving upward and analyzing each layer in turn, curiosity is effectively reading the geological record from bottom to top, tracking how conditions in the crater changed over time. The results show a transition from the wet, habitable lake environment at the base to increasingly dry, oxidizing conditions higher up. Mars was drying out, and the rocks record that transition with stunning clarity. Perseverance is similar in size and design to Curiosity, but carries a different instrument suite optimized for the search for biosignatures and for the collection of samples. Its landing site, Jezero Crater, was chosen specifically because it contains one of the best preserved ancient river deltas on Mars. The delta is a layered fan of sediment deposited where a river entered the ancient lake that once filled the crater. On Earth, delta sediments are excellent at trapping and preserving organic material, including the remains of microorganisms. If life ever existed in the Jezero Lake, the delta is where its traces are most likely to be found. Perseverance has been systematically exploring the delta, drilling cores from promising rocks and sealing them in sample tubes that will be cached on the surface for future retrieval. The rover has already collected dozens of samples from a variety of rock types, including igneous rocks from the crater floor and sedimentary rocks from the delta. Analysis by the rover's onboard instruments has revealed the presence of organic molecules in several samples, though their origin, biological or otherwise, remains undetermined. The definitive analysis will have to wait for the samples returned to Earth. Ingenuity, the Mars helicopter, was designed as a technology demonstration intended to make a few short flights and prove that powered flight was possible in Mars's thin atmosphere. Mars's atmosphere is so thin, less than 1% of Earth's, that generating aerodynamic lift is extremely challenging. Ingenuity's rotor blades spin at about 2,400 revolutions per minute, roughly 5 times faster than a typical helicopter on Earth, to generate enough lift in the thin air. The helicopter weighs only 1.8 kilograms and stands about half a meter tall. Its initial mission was to make 5 flights over 30 days. It ended up making 72 flights over nearly 3 years, covering a total distance of over 17 kilometers and reaching altitudes of up to 24 meters. It served as an aerial scout for Perseverance, surveying terrain ahead of the rover and identifying scientifically interesting targets. Ingenuity's mission ended in January 2024 when one of its rotor blades was damaged during landing. But its extraordinary success has already led to plans for larger, more capable rotorcraft on future Mars missions. The operational orbiters include NASA's Mars Reconnaissance Orbiter, which has been mapping and monitoring the surface since 2006, NASA's MAVEN, which studies the upper atmosphere and atmospheric loss, and the European Space Agency's Mars Express and Trace Gas Orbiter. China's Zhurong rover, which landed in May 2021, operated for about 1 Earth year before entering hibernation and has not been heard from since India's Mars Orbiter mission, launched in 2013, operated until 2022 before running out of fuel. Let me talk about the future. What comes next for Mars exploration, and what are the prospects for human missions? The next major step in robotic exploration is the Mars Sample Return Campaign, an ambitious and technically challenging endeavor to retrieve the samples that Perseverance is collecting and bring them back to Earth. The original plan, developed jointly by NASA and ESA, involved multiple spacecraft, a lander that would carry a small rocket called the Mars Ascent Vehicle, a fetch rover to retrieve Perseverance's sample tubes and load them into the rocket, and an orbiter to capture the sample container in Mars orbit and carry it back to Earth. The total cost was estimated at over $10 billion, and the timeline stretched into the 2030s budget constraints, and technical challenges have led to significant redesigns, with NASA soliciting alternative approaches from the private sector. SpaceX, among others, has proposed using its Starship vehicle to simplify the architecture. The details are still evolving, but the scientific community is nearly unanimous that returning Martian samples to Earth is the highest priority goal in planetary science. The analytical capabilities of terrestrial laboratories, electron microscopes, mass spectrometers, synchrotron X-ray sources, and dozens of other instruments far exceed what can be miniaturized and sent to Mars. A returned sample, even a small one, would yield orders of magnitude more information than any rover-based analysis. Beyond sample return, the next frontier is human exploration. Sending people to Mars is the most ambitious goal in the history of human spaceflight, and it is being actively pursued by both government agencies and private companies. The challenges are formidable. Mars is far away. At its closest approach, Mars is about 55 million kilometers from Earth. At its farthest, on the opposite side of the Sun, it is about 400 million kilometers away. Because both planets are orbiting the Sun at different rates, the distance changes continuously, and launch windows for efficient trajectories occur only about every 26 months. Using current propulsion technology, a one-way trip to Mars takes about 7 to 9 months. A round trip, including the time spent waiting on Mars for the planets to realign for the return journey, would take roughly 2 to 3 years. During the transit, astronauts would be exposed to two types of radiation: solar energetic particles produced by solar flares and coronal mass ejections, and galactic cosmic rays, high-energy particles from outside the solar system that penetrate spacecraft shielding. Both types of radiation increase the risk of cancer, damage the central nervous system, and can cause other health effects. On the Martian surface, the thin atmosphere and lack of magnetic field provide only modest protection, and the radiation dose, while lower than in deep space, is still significantly higher than on Earth. Over the course of a multi-year mission, the cumulative radiation dose would exceed the career limits currently set by NASA for astronauts by a significant margin. Developing better radiation shielding, whether through physical barriers, electromagnetic deflection, or pharmaceutical countermeasures, is one of the critical challenges for human Mars missions. The effects of reduced gravity are another concern. Mars's gravity is 38% of Earth's, and the transit in microgravity would last 7 to 9 months in each direction. On the International Space Station, astronauts in microgravity experience muscle atrophy, bone loss, cardiovascular deconditioning, fluid shifts that affect vision, and other physiological changes that are partially reversible with exercise but not entirely. Whether Mars's 38% gravity is sufficient to prevent these effects is unknown. No human has ever spent an extended period in partial gravity. The only partial gravity experience humans have is the brief time Apollo astronauts spent on the lunar surface at 16% of Earth's gravity, and those stays were too short to draw conclusions about long-term health effects. The psychological challenges of a Mars mission are equally daunting. A crew of perhaps 4 to 6 people would be confined to a relatively small spacecraft for months, millions of kilometers from home, with no possibility of rescue or resupply, facing a communications delay of up to 24 minutes each way that makes real-time conversation with mission control impossible. The isolation, confinement, monotony and stress of such a mission have no precedent in human experience. Antarctic winter-over cruise and submarine deployments offer partial analogues, but neither involves the absolute impossibility of return that a Mars transit crew would face during much of their journey. The psychological screening, training and support systems for Mars crews will need to be far more sophisticated than anything currently in use. The engineering challenges are enormous. A human Mars mission requires life support systems that can function reliably for years without resupply. A landing system capable of delivering tens of tons of payload to the Martian surface. A surface habitat that can protect the crew from radiation, temperature extremes and dust. A power source capable of generating enough electricity for life. Support, science operations and propellant production. And an ascent vehicle that can launch the crew off the Martian surface and into orbit for the return journey. Each of these systems presents significant technical challenges, and all of them must work perfectly in an environment where a failure can be fatal and repair options are severely limited. One of the most promising approaches to reducing the mass and cost of a Mars mission is in situ resource utilization, or ISRU, the idea of using Martian resources rather than bringing everything from Earth. The most critical application of ISRU is propellant production. The most likely return propellant is liquid methane and liquid oxygen, which can be produced on Mars from the carbon dioxide in the atmosphere and water extracted from subsurface ice. The chemistry is straightforward. The Sabatier reaction combines carbon dioxide with hydrogen to produce methane and water. Electrolysis splits water into hydrogen and oxygen. The hydrogen is recycled back into the Sabatier reactor, and the net inputs are carbon dioxide and energy. Carbon dioxide is available from the atmosphere. Water can be mined from subsurface ice deposits. Energy can be provided by nuclear reactors or large solar arrays. Perseverance carried a small technology demonstration called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which successfully produced oxygen from the Martian atmosphere by electrochemically splitting carbon dioxide molecules. MOXIE produced about 12 grams of oxygen per hour, roughly enough for a person to breathe for 20 minutes. A full-scale version would need to produce thousands of times more, but the proof of concept was established. SpaceX has been the most vocal proponent of human Mars missions, with CEO Elon Musk stating repeatedly that establishing a self-sustaining human settlement on Mars is the company's primary long-term goal. The Starship vehicle currently under development is designed from the ground up with Mars missions in mind. It is the largest and most powerful rocket ever built, standing about 120 meters tall with a payload capacity of over 100 tons to low Earth orbit. Its stainless steel construction, heat shield design, and in-orbit refueling architecture are all driven by the requirements of Mars transit. Musk's stated timeline for the first crewed landing has slipped repeatedly, from an initial target of 2024 to more recent suggestions of the late 2020s or early 2030s. But the development of Starship continues at a rapid pace, with test flights occurring regularly, and each one demonstrating increasing capability. NASA's current plans for human Mars exploration are less specific in timeline but more detailed in the technical architecture. The agency's Moon to Mars plan envisions using the Artemis program's lunar missions as a stepping stone, testing systems and operations on the Moon before committing to the longer and riskier Mars journey. The Deep Space Gateway, a small space station in lunar orbit, is intended to serve as a test bed for systems that will eventually be used for Mars transit, including life support, radiation monitoring, and deep space operations procedures. NASA has not set a firm date for a crewed Mars mission, with estimates generally falling in the late 2030s to 2040s, depending on funding and technology development. Other nations are also interested. China has expressed ambitions for crewed Mars missions, potentially in the 2030s or 2040s, following a program of robotic precursor missions that began with the Tianwen-1 orbiter and Zhurong rover in 2021. The European Space Agency has Mars sample return as a high priority and participates in technology development for future human missions. The United Arab Emirates, India, and Japan all have Mars programs of varying ambition and capability. The question of whether humans should go to Mars is separate from the question of whether they can. The case for human exploration rests on several arguments. First, humans are vastly more capable explorers than robots. A trained geologist on the surface of Mars could accomplish in a day what a rover takes months to do. Human judgment, flexibility, and physical dexterity enable scientific investigations that are simply impossible with remote-controlled machines operating on a 24-minute communications delay. Second, human Mars exploration would inspire public engagement with science and technology in a way that robotic missions, however successful, cannot match. The Apollo program is often cited as a model. Third, establishing a human presence on Mars would make humanity a multi-planet species, providing a backup for civilization against existential risks, from asteroid impacts to pandemic disease to self-inflicted catastrophe. This argument is more philosophical than scientific, but it resonates with many people who see planetary expansion as a natural and necessary extension of human exploration. The case against, or at least for caution, rests on the enormous cost, the significant risks to crew health and safety, the questionable ethics of exposing people to radiation levels that exceed current safety standards, and the possibility that robotic missions can accomplish the science more cost-effectively. There are also concerns about planetary protection. The risk that human explorers might contaminate Mars with terrestrial microorganisms, making it impossible to determine whether any life subsequently detected is native Martian life or Earth life that hitched a ride. This concern is particularly acute for the subsurface, where liquid water might exist and where terrestrial contamination could potentially establish itself and spread. The planetary protection question cuts both ways. There's also the question of whether Martian material brought back to Earth could pose a biological hazard, whether it might contain organisms that could harm terrestrial ecosystems. The probability of this is considered extremely low by most scientists, but it is not zero, and the consequences of getting it wrong could be catastrophic. Any Mars sample return mission will include stringent containment protocols to ensure that Martian material is handled in a facility with the highest level of biosafety until it can be demonstrated to be safe. Let me talk about what it would be like to actually live on Mars, because this question, once purely speculative, is increasingly becoming one of engineering and planning. If you were standing on the surface of Mars in a spacesuit and looked around, what would you see? The landscape would depend on where you were, of course, just as it does on Earth. If you were in the northern lowlands, you might see a flat, reddish-brown plain extending in every direction to a horizon that would seem slightly closer than you are used to, because Mars is smaller than Earth and curves away more sharply. The sky would be a butterscotch or salmon pink during the day, colored by the fine dust suspended in the atmosphere. At sunset, the colors would reverse. The sky near the setting sun would turn blue, because the dust particles in the Martian atmosphere scatter red light more than blue light, the opposite of what happens on Earth. Martian sunsets are blue. This is one of those facts about Mars that sounds like it should be fiction but is real, documented by multiple rovers and landers. If you were near the equator, midday temperatures might reach a few degrees above freezing in summer, but by nightfall the temperature would plunge to -70 or lower. You would need a heated suit, insulated against the cold and pressurized against the near vacuum of the atmosphere. The suit would need to supply breathable air, since the atmosphere is almost entirely carbon dioxide with only 0.16% oxygen. You could not breathe Martian air for even a few seconds. Your lungs would struggle against the near vacuum, and even if the pressure were somehow sufficient, the carbon dioxide concentration would render you unconscious within minutes and dead shortly after. The silence would be striking. Sound waves travel through air, and Mars has very little air. The atmosphere is too thin to carry sound efficiently. Sounds would be muffled. Higher-pitched sounds would be attenuated more than lower-pitched sounds, and the overall experience would be eerily quiet compared to anywhere on Earth. The Perseverance rover carries microphones that have recorded the sounds of Mars, including the thin whisper of the Martian wind, the crackle of its laser hitting rock, and the buzzing whir of Ingenuity's rotor blades. These are the first sounds ever recorded on another planet, and they are strange and spare and slightly alien. The gravity would feel odd. At 38% of Earth's gravity, you would weigh only about a third of what you weigh at home. You could jump higher, throw farther, lift heavier objects. Movement would feel buoyant, almost dreamlike, though the mass of your spacesuit would temper the sensation. Experience from Apollo astronauts on the Moon at 16% gravity suggests that walking in reduced gravity is awkward at first but adaptable, and that a bounding, loping gait becomes natural after some practice. Mars's 38% gravity would be easier to adapt to than the Moon's 16%. Enough gravity to maintain a sense of up and down and to keep objects on tables without restraints, but low enough to require new movement habits. The length of the day would feel familiar. A Martian sol, as the Martian day is called, is 24 hours, 37 minutes and 22 seconds, so close to an Earth day that the difference would be barely noticeable. Every sol would start about 37 minutes later than the previous one relative to an Earth clock, and over the course of a month your schedule would drift by about 18 hours. Mission controllers on Earth who try to synchronize their work schedule with Martian time find this drift exhausting, and during the early days of rover missions, entire teams shifted their sleep schedules to match Mars time, living in a perpetual state of mild jet lag. For permanent settlers, this would not be an issue. You would simply live on Mars time and let Earth figure itself out. A permanent settlement on Mars would need to solve several fundamental problems: shelter, air, water, food, energy, radiation protection, psychological sustainability. Each of these is solvable in principle, but enormously challenging in practice. Shelter could take many forms. The simplest approach would be to use the spacecraft itself as a habitat, supplemented by inflatable modules or rigid structures. More advanced concepts involve using Martian regolith, the loose surface material, as building material. Regolith could be sintered or melted into bricks using focused solar energy, or processed into a concrete-like material using Martian water and chemical binders. Some proposals envision building habitats underground, in lava tubes, the natural tunnels left behind by ancient volcanic lava flows. Mars has several regions where the ceilings of large lava tubes appear to have collapsed, forming chains of pits called skylights that could provide access to intact tunnel systems below. A habitat inside a lava tube would be naturally shielded from radiation by the overlying rock, protected from temperature extremes by the insulating properties of the surrounding material, and potentially large enough to accommodate substantial structures. Some terrestrial lava tubes are hundreds of meters wide and many kilometers long, and Martian lava tubes formed in lower gravity could be even larger. Air would be produced by ISRU systems, extracting oxygen from carbon dioxide in the atmosphere using electrolysis or other methods. Nitrogen, which makes up about 2.7% of the Martian atmosphere, could be extracted and mixed with the oxygen to create a breathable nitrogen-oxygen atmosphere similar to Earth's. The small amount of argon in the atmosphere is chemically inert and can be included without harm. Water would be mined from subsurface ice deposits, of which there appear to be enormous quantities at mid to high latitudes. The ice could be melted, purified, and used for drinking, agriculture, hygiene, and industrial processes, including propellant production. Water recycling systems, similar to those used on the International Space Station, would reclaim water from waste streams and reduce the total amount that needs to be mined. Food is one of the most difficult challenges. Transporting food from Earth for a permanent settlement is impractical. Each person requires roughly 2,000 to 2,500 calories per day, and food is heavy and bulky. A self-sustaining settlement would need to grow its own food, which means agriculture. Martian agriculture would need to be conducted in enclosed greenhouses with controlled atmosphere, temperature, lighting, and irrigation. The Martian soil is not directly suitable for plant growth. It lacks organic matter and nitrogen, and it contains perchlorates that are toxic to most plants and to humans. However, experiments have shown that simulated Martian regolith, after removal of perchlorates and supplementation with nutrients, can support plant growth. The lower gravity might affect plant development in ways that are not yet understood, and the reduced sunlight. Mars receives about 43% as much solar energy per unit area as Earth would require supplemental lighting for many crops. Energy on Mars could come from solar panels or nuclear reactors. Solar power is viable but limited by the lower solar flux, by dust accumulation on panels, and by the 12-hour nights. A nuclear fission reactor, similar in concept to small modular reactors being developed on Earth, would provide reliable continuous power regardless of weather or time of day, and is generally considered the most practical power source for a Mars settlement. NASA has been developing a small fission power system called kilopower, designed to produce about 10 kilowatts of electrical power from a uranium-235 reactor about the size of a trash can. A settlement would likely need several such reactors or a larger system to meet its power needs. The psychological challenges of living on Mars are difficult to overestimate. The settlers would be more isolated than any humans in history. Communication with Earth would involve a delay of 3 to 22 minutes each way, depending on the planet's positions, making real-time conversation impossible. Video calls would be replaced by something more like email, a series of recorded messages sent back and forth with significant delays. The settlement would need to be largely self-sufficient because resupply from Earth would take months and could only be launched during the biennial launch windows. In an emergency, there would be no rescue. Medical care would be limited to whatever equipment and expertise the settlers brought with them. Social dynamics in a small, isolated group under stress would require careful management. Studies of Antarctic research stations, submarine crews, and simulated Mars missions have consistently shown that interpersonal conflict, boredom, depression, and sleep disruption are major challenges in isolated, confined environments. And yet, for all these challenges, there is something undeniably compelling about the idea of humans on Mars. Not just visiting, but living there, building there, making it a second home for our species. The urge is partly scientific. There are questions about Mars that can only be answered by people on the ground, with the judgment and flexibility that robots lack. It is partly philosophical. The idea that humanity could extend its reach beyond one planet, could ensure its survival against the kind of catastrophe that ended the dinosaurs, touches something deep in the human psyche. And it is partly the simple ancient human drive to explore, to go beyond the horizon, to see what is on the other side of the mountain. Mars is the mountain, it is the next horizon, it is the most accessible other world in the solar system on which humans could establish a permanent presence. Venus is too hot, Mercury is too close to the Sun, the moons of Jupiter and Saturn are too far and too radiation blasted, at least with current technology. The moon is closer and easier to reach, but it is airless and waterless and geologically dead, offering fewer resources for long-term settlement than Mars. Mars has air, thin but present and rich in carbon dioxide that can be converted to oxygen and fuel. It has water frozen but abundant. It has a day almost identical to Earth's. It has seasons. It has geology. It has weather. It has a history of habitability. It is the most Earth-like world we know of, and it is waiting. There's a photograph taken by the Curiosity rover that I think about often. It shows the sun setting behind the rim of Gale crater, the sky turning blue near the horizon, the last light of day filtering through the thin Martian atmosphere. The image is simultaneously beautiful and desolate. It shows a world that is familiar enough to be recognized as a landscape, a horizon, a sunset, but alien enough to be unsettling. The colors are wrong, the sky is wrong, the silence, which you can almost feel in the photograph, even though photographs carry no sound, is wrong. Everything about it says, this is not home, and yet it is a place, a real place with real rocks and real dust and a real sun setting behind a real horizon. A place that robots have touched and photographed and drilled into and driven across. A place that within the lifetimes of people alive today, humans may stand on and look around and see with their own eyes what Curiosity saw through its cameras. Mars is not just a planet, it is a mirror. It shows us what can happen to a world that starts with many of the same ingredients as Earth, but follows a different path. It shows us that habitability is not guaranteed, that atmospheres can be lost, that oceans can vanish, that a world can die, or at least sleep so deeply that it appears dead. It shows us that the conditions we take for granted on Earth, the thick atmosphere, the liquid water, the magnetic field, the active geology, are not inevitable consequences of being a rocky planet, but are contingent, dependent on size and composition and distance from the Sun and the accidents of early planetary history. Mars also shows us something about ourselves. It shows us that we are the kind of species that builds telescopes to see red dots in the sky, that designs rockets to send machines to those red dots, that programs those machines to drive across alien landscapes and drill into alien rocks and photograph alien sunsets and send the images back across millions of kilometers of empty space so that we can look at them and wonder. We are the kind of species that, having done all that, then asks, can we go there ourselves? Can we live there? Can we make it a home? The answer almost certainly is yes, not easily, not cheaply, not without risk and sacrifice and failure and hard-won lessons, but yes, the physics allows it. The engineering is within reach, the resources are there, frozen in the ground and floating in the thin, cold air. The question is not whether humans can go to Mars. The question is when and whether we will have the will and the wisdom to do it well. The red dot in the night sky has been watching us for as long as we have been watching it. It was there before humans had language, before we had fire, before we had names for the points of light that moved against the fixed stars. It was there when the Babylonians first tracked its wandering path across the zodiac, when the Greeks called it Aries and the Romans called it Mars, when Percival Lowell sketched canals that did not exist and H.G. Wells imagined invaders that never came. It was there when Mariner 4 sent back 22 photographs that shattered our illusions, and when Mariner 9 sent back thousands that replaced those illusions with something far more interesting. It was there when Viking searched for life and found ambiguity, when spirit and opportunity drove across its surface for years, when curiosity found the dried bed of an ancient lake, when perseverance began collecting samples that may one day be the first pieces of another planet to be studied on Earth. It is there now tonight, above some horizon, visible to anyone who knows where to look. A small, steady, rust-colored light in a sky full of stars. It does not flicker, it does not twinkle, or at least not as much as the stars do, because it is closer and its light passes through less atmosphere. It just shines quiet and patient and red, waiting. Mars has waited for 4.6 billion years. It can wait a little longer, but maybe not much longer. The machines are already there, the plans are being drawn, the rockets are being built. The first generation of humans who will walk on Mars may already have been born. They may be children now, learning about the red planet in school, looking up at the night sky with the same curiosity that drove every astronomer and engineer and dreamer who came before them. They do not yet know that Mars will be their destination. Mars does not know either. But the trajectory is set. The slow curve of human ambition bending toward another world, and the distance, while still vast, is closing. 4 billion years ago, Mars may have been a world of rivers and lakes and rain, a world where life might have stirred in warm, shallow waters, where the sky was thicker and the sun was closer and the planet was young and full of possibility. Today it is a frozen desert, silent and still, its rivers gone, its atmosphere dwindled, its surface scarred by radiation and oxidized to rust. But it is not dead, it is not empty, it is not finished. It is the most studied, most mapped, most photographed, most analyzed planet in the solar system besides our own, and every new mission reveals something unexpected, something that changes the picture, something that raises new questions even as it answers old ones. Mars is the next chapter in the story of human exploration. It is the test case for our ability to live beyond Earth. It is the laboratory for understanding planetary habitability, atmospheric evolution, and the conditions for life. It is the destination that will define the next era of spaceflight, the next generation of scientists and engineers, the next great adventure of our species. And it starts with that red dot in the sky, that quiet, patient, rust-colored light that has been there since before we had eyes to see it, since before we had brains to wonder about it, since before we were anything at all. It was there when we were microbes in the ocean. It was there when we were fish crawling onto land. It was there when we were primates swinging through trees. It was there when we looked up for the first time and asked, "What is that?" We know the answer now, not completely, not perfectly. There are still enormous gaps in our understanding, still questions that will take decades or centuries to resolve, still surprises waiting in the rocks and the ice and the thin, cold air. But we know enough. We know that Mars is a world. A real, physical, tangible world with mountains and canyons and polar caps and dust storms and a sky that turns blue at sunset. A world that was once warmer and wetter and might once have harbored life. A world that is cold and dry and hostile now, but that still holds water in its ice and carbon in its air and iron in its rust. A world that robots have explored and that humans will follow. Everything you need to know about Mars is this. It is a world that was born with possibility, that lost most of that possibility to the pitiless physics of size and distance and time, and that retains even now beneath its rust and dust and silence the faintest echo of what it once was and the faintest promise of what it might become. It is the closest thing to Earth that the solar system has to offer, and it is calling not with sound. Mars is too thin-aired and too far away for us to hear it, but with light, that quiet, steady, rust-colored light shining in the night sky, patient as it has always been, waiting for us to come, and we are coming. Slowly, cautiously, with robots first and people after. With questions and instruments and the stubborn, restless curiosity that has driven our species since we first looked up from the African savanna and wondered what was beyond the next hill. Mars is beyond the next hill. It has always been beyond the next hill. And now, for the first time in 4.5 billion years, something from this planet is reaching out to touch it. The red planet waits. It has been waiting since before there was anyone to notice it. It will not have to wait much longer. And when we finally arrive, when the first human boot presses into the rust-red dust and leaves a print that will last for millions of years in the windless calm of a Martian plain, we will look up at the sky and see, hanging above the horizon, a bright blue dot, Earth home, the place where we started. The place where, one ordinary day, a small, curious species of primate looked up at a red point of light in the sky and decided, against all odds and reason and caution, to go there. That is everything you need to know about Mars, and it is only the beginning of everything we will learn.